Okay, hello everyone. My name is Yeil Kwon. I'm the assistant professor in mathematics departments at UCA, University of the Central Arkansas. I am specialized in the statistics and probability. But after I joined the UCA, I worked with my colleagues, the math educators. We are working on about the mathematic education, especially statistics and the probability. My talk is about how to approach the probability problems with the technologies. I'm going to use the example for the broken stick problems, which is very well known and very easy problem in probability. The main point is, anyway, the probability is very hard part to teach to students. That is because most likely the probability problem requires a lot of the mathematical skills. So if we have a students having a major mathematics or statistics, we can approach using that kind of approach, but we cannot use that mathematical approach to every students. And recently, you know that probability and statistics becomes a very important portion in our modern life. So we have to think about how can we deliver the probabilistic knowledge to the students a little more efficient way. One of the very attractive candidates to deliver this probability problem is using the technology, especially the simulation. Because basically the probability comes from the many replicative experiments, but we have to solve them mathematical way because we cannot do that kind of experiment physically. But many cases we can do that kind of experiment using the simulation study. And this simulation study does not require many, much portion of the mathematical knowledge, just using intuition and very basic, especially in this question, the geometrical knowledge. It is very easy to approach to these problems. So I just want to show comparing the traditional and simulation-based teaching method. So broken stick problem is, the idea is very simple. We have a stick and dropped on the floor and breaks at random into 3 pieces. Then what is the probability that these 3 parts of the broken stick form a triangle? So if we have the 1,000 of the sticks, then we can drop them and we count how many cases we can make a triangle. It is impossible physically. So we have, suppose that, just imagine we have a length 1 stick here. And randomly this stick has been broken, like here and here we have 3 parts. And to make our calculation easier, let's think about the total length is 1. And then we want to ask, what is the probability that the 3 parts of this broken stick form a triangle like this? Not every case we can make this triangle. For example, if A, B are extremely small, then we cannot make a triangle. So this is just the traditional approach. You don't have to look at this one too much. I just want to show that how complicated it is. So we have to solve many inequalities and equations. And by solving this integral, we can get the probability. So we can see this problem answer has just 1/4. So if you have a random stick and the probability that we have a triangle by using this broken sticks is just 1/4. That is the theoretical solution. But think about this algorithm. This use only the information of this part. That means the sum of the 2 sides, is greater than the other, then we can make a triangle. This is a basic knowledge of the geometry. Only using this, without using this kind of complicated calculus or the system of the linear inequalities. We don't have to use that. Just using this, we can repeat the experiments many times, like 1,000 times. We can get the probability. Think about the second way, the second example. Then specifically, what is the probability that we make an acute triangle? Acute triangle means all of the three angles are less than 90 degrees. Then based on this geometric knowledge, we have to solve this much complicated inequalities of the rational functions. And then we have to do this much complicated, again, the integrals. And we have the mathematical solution like this, 3 times log 8 over e squared. So we have to, if you want to teach this to students, then we have to teach geometry, rational function, log exponential function, system of the nonlinear inequalities, and calculus, especially the double integral. This is calculus 2 parts. But if we apply the simulation-based approach, only thing we have changed is this one. The other parts are exactly same to the previous example. Only thing we have to change is this part. Then we can get the solution. Third one, what about we want to find out the probability that we have the triangle with area is less than 0.03, for example. Then here we have to use the Harris formula because we have 3 sides, the length of the sides. Using this, again, we have to use this much complicated mathematics and a lot more complex math work we have to do. So more than the previous example, we have to teach the radical function equation and numerical analysis and advanced double integral parts. But without doing this, if we use the simulation base, only thing we have changed is this. Using the Harris formula, the area is less than 0.03. That's it. So if you compare those 3 algorithms, only difference is just this part. Sum of the 2 sides is greater than the other, the last one, and the sum of the square is greater than the other square, and the area is less than 0.03. That's it. So by using this algorithm, we can make many various alternative questions we can deliver to the students. So this is our, it doesn't matter whatever programming language we use, but R is very popular because this is free and very easy to learn. So as you can see here, we need is just to define the variables and generate X and Y, and we have 3 sides. And this is the question 1, question 2, question 3. That's it. And then you can calculate this probability. So without addressing this mathematics, we can use this kind of approach to like middle school students, high school students, or the college students, not in the mathematics departments. And this is very intuitive. And this kind of calculation makes students digress. So students in many cases forget what I'm doing now, what I'm solving this problem, because they have to solve this very complicated calculations. So this is a result of simulation. So this is a case that we have 1,000 case. And this is 5,000. So 1,000 repetition, we have this black line is the theoretical solution, not very close to the theoretical solution, these 2 cases. But if we increase the number of simulation, then we have much more closer, and we make a 10,000, then we can approach to this. And the time calculate this takes less than 1 second. So this is not only very fun, and many students have many students can be motivated by this kind of approach. So this is the simulation result, another simulation result. So as we increase this number of replications, number of sample size, we have much more accurate result like this. So conclusion is, we know that as a mathematics faculty members, I know that the traditional mathematical approach is very important. So I still address this kind of approach to my graduate students and upper level students. But when we need to teach very basic problems of the probability to like the students in business or psychology, nursing, whatever departments, we don't have to employ too much complex mathematical work. And by using this simulation approach, we can capture their attention and we can address the main idea of the probability. So it is easy to access, fun, and very intuitive. Of course, we can extend our discussion to much more various questions like advanced geometric probability and very interesting historical probability problems like a Monty Hall problem and gambler's ring. And we can have a simulation for the wildfire spread or the infectious disease or the virus spread. We can make simulation like this. Okay. I hurried too much. If you have any question, I want answer for your question.